Hello, everyone. In the fourth episode of the Astro AI podcast, we are talking about the realities of the big claims of room temperature superconductors that can potentially change the way we use technology, and it has big implications in quantum computing as well. And we talk about the big quantum realm, like a big research has just come into picture, like the quantum entanglement of photons has been captured in real time. So what it can do for us. So we'll talk about the quantum mechanics, quantum realm in this episode as well. So just watch the whole episode, sit tight, and do listen or watch this podcast in full. Now we talk about a very important and potentially world-changing story that came our way. Before that, like a little bit of background. It's about superconductors. So superconductors are usually used in supercomputers or quantum computers. So you might have seen the pictures of quantum computer, like all like a oddly shaped computer, like a tall gold bronze colored computer that works on superconductors. Superconductors usually work at very low temperature. That's like the lowest temperature in the entire universe, like 0 Kelvin. So that is close to minus 270 degrees Celsius on a Celsius scale. So that requires a lot of energy, a lot of resources to manage, to maintain, and like specialized facilities. In Seoul, in South Korea, there was like a quantum energy research center. They actually developed a compound which is called LK99, which was a compound made from copper, lead, phosphorus, and oxygen. And they termed it as room temperature superconductor. So, like I said, superconductors only work at very low temperature and high pressure. If you found or you formulate a compound that could work in a room temperature setting, imagine the applications of that. We can make quantum computers for potentially everyone. Like in homes, we can have quantum computers in the next 10 to 20 years, which would not have been possible if quantum computers use a superconductor requiring 0 Kelvin and very extreme pressure. So that way, like if they try to make this compound LK99 and they claimed it that it's a superconductor, works at normal pressure and room temperature. Even it works at 127 up to 127 degrees Celsius, which is like a high temperature. So it can even be used outdoors in a factory setting, like in a manufacturing setting as well. So that was like a very huge news. Like if it is true, it could actually change everything. It could change the entire world, like the way we do our technology. Everything could have changed.
I think what would help probably to our viewers is why is superconductor, like what is it conducting? I think the main answer is electricity, right?
Yes.
Um,
So
and why is it so important to have to conduct electricity at such a, I guess, efficiency or high
yeah.
efficiency, I guess,
Okay.
and
Yeah.
speed. So
I'll I'll
uh,
come on that now. So very simple reason for that, and like superconductors are used basically in multiple settings, but here we are talking about quantum computers specifically. Why we need superconductors in quantum computers? Because the calculations that are happening, they happen with the help of photons or electrons. They are subatomic particles. When you take an atom, for example, and if you go into the atom, you would see
yeah.
the nucleus and the rotating electrons, that like everybody knows that, right? So and photons are particles that light is made of. So photons
Mhm.
and electrons are usually quantum computers use like they can also use photons, like recent research has claimed, but usually it's electrons, and those electrons must be in a
A
special
compound,
state,
okay.
in a special compound, in a superconductor. So superconductor, what it is, it conducts electricity. That is, electricity is nothing that just the flow of electrons in a straight
Mhm.
line, right?
Yeah.
So on and off switch, like the transistors do, on and off switch. And that's how computers, any computer work. So what superconductors do, they actually very precisely and very fast paced movement of electrons. And why we need like very low temperature and high pressure is like we don't want to waste any energy that is oozing out of those fast moving electrons.
Yeah.
Simply speaking. So we just want to keep it them like at lowest possible temperature, that no energy is disturbed, and the electrons are maintained in a quantum state. So again, there's like a very big debate, quantum mechanics. I'm making a full video on my channel, so watch that video when it comes out. But simply, quantum state is like when these electrons are in a superposition state. So superposition is, for example, if there is a 0 and there's 1, and normal computer bit is either at 0 or at 1, but quantum computer uses qubits. So these qubits, because they are in a superconductor, and these electrons, they are electrons essentially, but they are in a all the possible combinations of 0 and 1 at the same time. That's called superposition. So this property of quantum world, scientists take into account superposition, and that's how quantum computers are way faster than normal computers. They can do calculations in seconds, which like the world's fastest supercomputer would take 40 to 50 years. So that's why we need superconductors in quantum computers. And
And we
if
need
so,
quantum computing with AI applications. So all
yes,
of these,
huge implications.
yeah, model
Yeah, huge
training becomes super
implications of
fast.
quantum computer. Yes.
Yeah,
So if imagine now, imagine with all the information you have, if all that can be done at room temperature, how much money, how much energy would you save? And it can
yeah,
be placed in every household normal computer that we have. If
yeah,
But that's another debate. Quantum computers are not everyday computers. They are like for very different uses. They are not like, they cannot be used for normal day computing anyway. So but that's for another thing. But imagine like we have super quantum computer in every home if there was this kind of room temperature superconductor. But sadly, the claims were not true. They were right in their way, that it is conducting, it is levitating, it is showing resistivity, like very low resistivity and everything, all the characteristics of super conductors. But the problem was these kind of properties were because of the impurities in the material, the copper sulfide that they have. Because of these impurities, there was a sharp drop in electrical resistivity that
mm,
superconductors show, and the partial levitation over a magnet. So these kind of properties, which only superconductors show, this material was also showing, but only because of the impurity in its components. So this was sadly not a superconductor at room temperature, but just like a normal conductor. But it might have its own applications, but it's
mm.
definitely not a superconductor, sadly. But if it was
Okay.
true, it would have been world changing.
Yeah, that was debunked pretty fast
Yeah.
uh,
So
when this
I'll
came
link
out. Like,
I'll link the Nature article which debunked the claims of this. So just feel free to read that. It's not that difficult to read, and please read that, and how superconductors are different. Then I'll also
yeah,
leave some links and about quantum computers as well. So a lot of reading
yeah.
if
We'll
you are interested.
also have definitely future episodes on quantum computing itself.
Of course.
Dedicated
Yeah.
to it because it's such a vast and evolving field. I
Yeah.
think in one of the earlier podcast outside of this channel that we did, we talked about like future careers, and quantum computing is one of the
Yes.
careers that someone can pursue into like material science and of course physics. So
Yeah.
yeah, these are like non-tech field, non-IT kind of fields,
Non
if you want
IT.
to say
Yeah.
non-computer related stuff. So
Yeah. Kind of
uh,
hardware problems. Yeah.
yeah,
Hardware and
hardware
material science.
problems that
Yeah.
we need to solve for advancing a lot of these fields forward, like AI, of course. Then anything that would need more like insane amount of computing. For example, the probes that we send in outer spaces, I'm pretty sure you would need to control
Yes.
it even much more precisely and better. So
And
all
very
of
low
those,
temperature.
right, and very low
Very low
temperature,
temperature of
right,
space. Yeah.
right.
So
So yeah,
they have like huge implications. Like if someone is interested in material science, like Pritul said, It's a huge in demand field, like major implication. And if you can develop room temperature superconductor, the true room temperature superconductor, you can actually win a Nobel Prize in chemistry. I'm
Oh wow.
100% certain. Very important segue from that is fascinating discovery has been made, and not discovery, it's kind of a demonstration. In the very first time, like again, a study was published in Nature, one of the journals in Nature Photomics, I think, and it demonstrates the quantum entanglement of photons in real time. Again, we were talking about the quantum world. Quantum world is very different than our real macro world, right? Why I'm saying that, because background is really important. Like otherwise, our viewers will not be able to appreciate this information. So in our macro world, like what we live in, we can touch things, we can see things, we can see the distance, the position, the weight and the length and the size and shape of everything, right? We can touch and feel and everything. But in quantum realm, the quantum field, uh, that's not how things work. Everything works in approximations, everything works on possibilities, probabilities. So in quantum realm, because quantum is like very subatomic, like below the atom range, that's called that's basically quantum, that's not the name itself. So at subatomic level, things work very differently, completely different than rest of the world. So where things work in probabilities, the possibilities, like, and where we represent everything, like these particles I was talking about, the electrons and photons, just because we cannot certainly say where the photon and where the what's the position and what's the momentum of that particular particle at the particular time, which is called uncertainty principle. I'm sure if you had science, 10th grade or 12th grade science, you must have heard about uncertainty principle, Heisenberg's uncertainty principle, which states that the quantum particles, like we cannot accurately predict the position and momentum of a subatomic particle like a photon or electron, because it's too small that it's basically everywhere at the same time. So
Mm.
that's why we it's very difficult, and it's not about our ability to uh, analyze or observe. It's the property of the quantum world. In the future, if we determine like very sophisticated equipment, even then we'll not be able to do that, we'll not be able to identify that. It's the inherent nature of the quantum world. So what it happens in quantum world, like superposition I was talking about, like one particle remains in all possible states. So the uncertainty principle also adheres to this, like superposition and uncertainty, like which tells us that in quantum world we cannot ascertain anything with certainty. So one of the properties of quantum world is called quantum entanglement. So suppose you take two photons, like light particles. So light is a wave and light is also a particle. So that behaves with a dual nature. You must have heard. So that's why we represent these photons with a wave function, right? So what happens, like if you take two protons, like a pair of proton, and
Proton
if
or
you
photon? Photon.
photon, sorry, my
Photon.
bad, photon, not proton. Protons are not fundamental particles, they are not
Yeah.
fundamental particles, we'll talk about it in later episode maybe. So two photons if you take, and if you connect them, which is called quantum entanglement, and if you then leave at infinite distance between each other, and if you change one, the properties of the other are automatically changed no matter what's the distance. Theoretically, if you leave one at here and the other one at other part of the galaxy, it will still behave the same because they are connected, which is called quantum entanglement, which is another fascinating property of quantum world. So what happens, like if you change one, the other is also changed. So that has been observed in real time, like in of course you cannot see photons or you cannot see electrons with whatever instrument you have in present or future because they don't have any mass. They just have either charge or no charge, but they are like massless particles. So you cannot directly observe them. You only can indirectly observe them through their actions, what they are doing. So this quantum entanglement, what we are talking about, has been observed in real time. So what they did, I will also pin the article here. So what they did, they recreated image of the yin yang, and
Mhm.
for one photon representative of one, and the image of the yin yang was recreated for another photon. So one, you change something in one photon, and for other it is changed automatically. So if it's still confusing, it might be. So just consider it with a very simple example. They have also given that example in the paper, that suppose you have a pair of shoe, and if you lose one shoe, and for example, an alien come and they take one of your shoe and far off the Milky Way. So if you see one shoe, you will immediately see what's the properties of the other shoe. For example, if they have taken the right shoe, you would know, oh, you are left with the left shoe, and now the other one would be almost 100% certainty would be right one. Same thing can
Mhm.
be said about the color, and the orientation, the position, momentum, everything. So just replace shoe with photon. So that's how quantum entanglement work in simplistic terms. And
Okay.
that's what they actually visual captured, like demonstrated in real time, which is a very fascinating thing.
What are the applications that could become like
So the
mainstream? I know
yeah,
quantum
so
is
why it's a
already, yeah, very,
yeah,
very
why it's a
hard
big
field,
deal.
right?
Yeah, it's a big deal because quantum field or quantum mechanics is used not only in quantum computers, it is used in several fields like laser, like satellites, transistors of the chip that you use in almost any device. So everything uses the quantum field, quantum mechanics in its principle. So if we can observe, because quantum entanglement was thought to be the process, but there was like very time consuming process for the real time capture, but they have made it like very simplistic, and they have made it very ordered. So this research is also like kind of a big deal. So because if we can understand quantum entanglement in detail, we can understand the quantum processes in detail, and that can in turn make the technology better for everyone, not just
Right.
quantum computer, the transistors and the lasers, and whatever we do, LEDs, the satellite positioning, everything can be changed.
Yeah. All right, that's it for today's episode. Don't forget to like, subscribe, and share the video.